Okay, so today we're going to continue our study of groups and then dive into subgroups. I want to start by introducing a famous group called the Klein 4 group. It's in our text, but just to get it put up here, right? Has a standard symbol K4, and it has, because it has 4 elements. So we'll list the Cayley table for this group. We're going to call E the identity, so it's easy to do that, right? So this must be E times E is E, or E star E, A, B, C, and going down, because the identity works on both sides. This must be A, B, C. Now I'm going to make just one choice that will really determine the rest of the table. I'm going to let A star A be the identity. And now, what choice do I have for B star A? It can't be A, it can't be E, and it can't be B, right? Otherwise it had duplicates, so it must be C. And then, what's the only unused item in this column? B, right? And we can fill it out with similar reasoning, but I don't want to spend all my time on reasoning here. That's going to be E, that's going to be E, A, and so that's the Cayley table that gives us the group operations. First thing we're going to do is show it's a group. What do we need to show it's a group?
For A cross B, should that be B?
AE?
No, the AB.
C. Thank you. I'm looking too close.
And would A cross C be? Yeah.
Yeah. Backwards. That's better. Yes. Okay, so now, otherwise it wouldn't be a group, right? So now it's a group. What do we need for a group? Identity. Well, E is the identity by inspection. So we have identity. Everybody needs an inverse. E inverse is always. What do I multiply the identity by to get the identity? So itself. What would A inverse be in this case? What do I multiply A by to get the identity? A, right? And then what do I multiply B by to get the identity? B. And what do I multiply C by? C. So each element is its own inverse. Everybody's got an inverse, so I have inverses. Identity, inverses, what else do I need for a group? Associativity. Well, that's a lot of work, right? I'd have to try them all. Let's just do one of them. It would take too much time to try to calculate all of them. Let's try A star B star C. Because it reminds us how to calculate in a group. Well, the first thing I do is work inside parentheses like always, so that's A star. What is B star C? Remember, I use a Cayley table, I start here, right? So BC is A. And A star A is the identity. How about the quantity A star B star C? Well, what is A star B? A, B is C. And that's the identity. So it works in that case, and you can work out the other cases. So This is just one case, doesn't prove associativity, but we do have associativity. We have that this operator is associative. So identity inverse is associative. This is indeed a group, which is why it's called the Klein 4 group. It's a group with 4 elements, but something's different about this than the other small groups we've studied. And I want to use that to introduce a new idea for groups that will carry on to our subgroup discussion today. If a to the n is the identity, yes?
I thought we had a proof closure also. We were proving if it was a group.
The table does that.
Okay.
It's kind of, right, every answer is one of the questions, right? But that's a good point. Yes, it is closed. Okay. If I put P in the table somewhere, it wouldn't be closed anymore, right? But yeah, so that's a good question. Okay. A to the n is e. What does that mean? Well, in groups, I can only use a positive integer power, right? I can't talk about a to the 1.7 like I can in real numbers, because this just really means operate a with itself n times, right? If a to the n is e, and n is the smallest value that does that, we say that the order of the element the smallest value that works. We say the order of A is n. Now, in this Klein group, what is the order of A? What would be the order of A? What's the smallest power of A that gives me the identity? 2. Good. A squared is A star A is the identity, so, and A isn't the identity, so the order is 2. What about B? 2. Yeah, because B star B is the identity in C. Every element, every non-identity element, right? The identity is always of order 1, right? Because e to the 1 is e, right? For any, because the identity is the identity. So, but all the other elements here are of order 2. And order will become an important consideration as we move forward with other groups. Okay, so this is the Klein group. I'm going to leave the Klein group up here and then give it the definition of a subgroup, because this one's a simple one to play with. And then we'll talk about other subgroups. So if G is a group, that really means G with an operator, right? Implied there has to be a binary operator over here. And S is a subset of G, right? In other words, a subset of the elements in G. I can always form a subset by picking some of them. S is a subgroup if S is a group. with the same operator. So that's the definition of a subgroup. It's a group contained in a group. Now we've already seen some of these, I think, so let's list some obvious ones by way of example. The real numbers with addition is a group. We proved that and showed that, right? Because 0 is the identity and minus x is the inverse of x and real addition is associative. Well, isn't it true that the rational numbers are a subset of the real numbers? Sure they are, right? And the rational numbers with the same definition of plus is a group, right? We showed that too. If I add two rational numbers, I get a rational number. 0 is a rational number, and the additive inverse of a rational number is a rational number. So by the definition here, since the rationals are contained in, as a subset, the real numbers, and they're a group with the same operation, they are actually, Q is actually a subgroup. Of R, with addition. Can you think of another subgroup that's also a subgroup of the rationals, based on our studies of groups? What's a set that's contained inside rationals? It's also a group with addition. The integers, sure. So we actually have a little chain, right? Z is contained in Q, is contained in R, and with addition, Z is a subgroup of Q, Q is a subgroup of R, the integers are also a subgroup of the reals. Because the integers are contained in the reals and they are a group with the same operator, addition. Okay. Let's look at finding subgroups of a Klein group. It's a little more concrete when you have a finite number of elements. How do I make subgroups? Well, I want my S. What's got to be in there, obviously, if it's going to be a group? E, the identity, right? Now let me throw in A and see if I have a subgroup. Now subgroups, we really have to worry about closure. So using the same operation, that is the same Cayley table, let's try to make a Cayley table with just these two elements and see if it works. That is, we need to use the same star with the same answers. Well, E star E is E. E star A is A. And A star E is A. And A star A is E. Is that a group?
Yes.
Well, it's certainly closed. Has identity. Everybody's got an inverse. E inverse is E and A inverse is A. So have inverses. And if we believe that this operator is associative, it comes along for free here. Because if I take any three of these and mix them, because they're already associative over here, I know they must be associative here. So we say for a subgroup, we always inherit associativity. Because the elements we're picking are already associative in the bigger group. Therefore, S is a subgroup. Of the Klein 4 group. Can you think of the smallest possible subgroup? Yeah, the identity by itself in any group is called the trivial subgroup. Because obviously, when I multiply the identity by itself, I get the identity, it's closed, it is its own inverse, and associativity is trivial when I've only got one element. That is E star, E star, E, doesn't matter how I do the parentheses. So there's two subgroups of the Klein 4 group. Can you think of another one that's obvious then by this construction? What would be another subgroup? It has to have the identity. It can't be A, so what else? Does B work? Sure. All I have to do is erase the A's in here and put B's, and I have the same structure, right? So there's a third one, which is the identity with C. All those are subgroups. I've got 4 subgroups. The trivial subgroup, this one, and that one. And the Cayley tables for these other two look just like this, because the elements are order 2, right? In other words, B star B is the identity. And what if I try to form a group this way? Call it S4. And I bring in the identity, A, and B. Well, what is A star B?
C.
I guess the whole thing, right? As soon as I add those to get closure, I'm back where I started. So that's not a subgroup, it's not closed. Because as soon as I operate A and B, I get C, which means I have the whole thing, right? So we've identified all the subgroups this way. So these are all the subgroups of the Klein group.
So in order for it to be a subgroup, the term has to be within the S.
Yes, because we're saying the subgroup is closed, right?
Mm-hmm.
So if I operate any 2 elements, I have to get an element.
Like
that's in
for
that
instance,
set back.
if S equaled BC, that wouldn't be a subgroup because you need identity in it.
Correct.
And you would need A.
Yes, because B star C is A.
Okay.
Yes. Good. All right, I think we have time for one definition before the camera dies. The definition of a subgroup is useful, but it's not very useful as a test whether something is a subgroup or not. The subgroup test if G is a group, and S is a subset of G, S is a subgroup, if the identity is in S, the identity of the original group. That's part 1. Part 2 is I need closure. As if I take any 2 elements in the subset, their product, their result of operating them together must also be, that's closure, must be in there. And one more thing, if G is in my subset, what else must be in there to make a group out of this? If it's a group, what's the obvious other requirement? It's inverse, good. Then G inverse must be in there also. In that set. So this is the subgroup test. It's a very practical test. If the identity is not in there, I'm done. If it's not closed, I'm done. It's not a subgroup. If the identity is in there and it's closed, and every element's inverse is also in the set, then I have a subgroup. That's the subgroup test. And this is a good place to pause.